My name is Abhimanyu Singh, and we were continuing with chapter number 2, polynomials. And if you remember from the last lecture, children, we have studied the meaning of the zeros theoretically and graphically. Theoretically, it would mean that 0 is a value of a polynomial at which the entire polynomial becomes 0, and graphically, it would mean that the meaning of the graphical meaning of the zeros is at what points on the x-axis the graph should intersect. That means the zeros graphically would mean the abscissa. They stand for the abscissa of the point of intersection of the graph with the x-axis. So after doing all those things, we will proceed towards exercise number 2.1. And in that case, children, you can see there are several graphs drawn in the book. In the first exercise, you can see, for example, I am taking graph number 3 of question number 1. This is x-axis, y-axis, and the graph goes like this. The graph is like this. So the question asks you find the number of zeros of px. So in order to find the number of zeros of px, you need to first determine how many times it intersects the x-axis. So 1, 2, 3. So this graph has 3 zeros, 3 distinct zeros for now, right? So let us take some other example. Part 6th. See, the graph goes like this. It touches the x-axis and then again moves up, and then it moves down, touches the x-axis, and then moves above the x-axis. So whether it intersects or it touches the x-axis, the abscissa of those points, the x-coordinate of those points will be the zeros of the polynomial. So again there are 3 zeros. So in such a way you can do the remaining 4 parts. The first part is very interesting. This is the Cartesian plane and the graph is a straight line. So it is a linear graph, linear polynomials graph it is, and hence since it doesn't touch the x-axis, so it will never have, it will have 0 zeros, right? So the number of zeros of this polynomial is 0 because it never touches x-axis. What zeros are? Zeros are the values which are the abscissa of the point of intersection of the x-axis with the graph. Now let us move towards exercise to this new topic, which is relationship between the zeros and the coefficients of the polynomial. So if you remember, children, we are talking about a quadratic polynomial because in the syllabus you have been confined towards learning only linear and quadratic polynomials. So let us take P of x, the quadratic polynomial P of x as ax square plus bx plus c with the complete set of conditions. A cannot be 0. If a is 0, x square, the second degree term vanishes, and therefore the polynomial gets reduced to linear polynomial, failing our purpose towards understanding the topic. After writing a is not equals to 0, let alpha and beta be real numbers. They are zeros of P of x. Now if they are the zeros, it would mean that keeping alpha in place of x, the polynomial is 0, right? The meaning of the 0 is, we have discussed it earlier in the last lecture, children. If you keep alpha in place of 0 everywhere, the entire polynomial is reduced to 0. Also, p at beta, alpha and beta are the letters of Greek alphabet, is also reduced to 0 because they are 0. So by definition of a 0, by definition p of alpha and p of beta is 0. Now if you recall, children, factor theorem of class 9th chapter 2, it says that a is a real number, and if p of a is 0, it would mean that x minus a is a factor of p of x. What is p of x? A polynomial of degree more than 1 or more than 1. So here also I can write x minus alpha, because p of alpha is 0, p of a is 0, x minus a, x minus alpha. In place of a, we will write alpha is a factor of your polynomial. Also, x minus beta is a factor of p of x. Now you have got two factors. If I say 2 and 3 are factors of 12, can the multiplication of these two prime numbers is a factor be called a factor of 12? Yes. So I can also write the product of these two individual factors to be the factor of p of x is also a factor of p of x, right? Because if you even take the 6 as the number, not 12, 2 into 3, which are the factors of 6, and 2 into 3, 2 and 3, and 2 into 3, both, all these three terms, 2, 3 and 6 are factors of 6, right? So that is what the meaning of this concept is. So I can write ax square, the entire polynomial, as the product of the individual polynomial. But we are missing out on one thing, children. We are missing out on one thing. What that thing is? Let us say the polynomial is of the kind, if I take the polynomial, I can multiply the entire polynomial by 2, right? This could give me another polynomial. That means on the graph paper, it could depict a different polynomial, a different parabola, but the factors by splitting the middle term, if you obtain the factors, they would remain the same. So here could be any constant, a real constant, it could be k, and then you can get different polynomials depending upon the value of k. So there exists a possibility that there would not be one always, there can exist k, and in fact k could be 1 but not always 1. K could be any real number, k could be any constant, k could be like 100. So again this would give you a different graph, but that graph will obviously pass through 2 and 3 always. Remember this, right? If there is 100, you can get such a graph, because if I draw the x-axis and 2 points over it, there are infinite number of graphs that can pass through the 2 points, infinite number of parabolas that can pass through the 2 points, but one thing is common between among all these numerous number of graphs is that they will pass through 2 and 3 of x-axis. But there could be infinite number of such graphs, and you never know which one of these could depict your polynomial, right? So we have to have certain room, for that constant. Let that constant be k. It could be a possibility that some common factor could be taken out and then it could be attached to the product of these two factors. Now, before proceeding further, why did I write this line, children? If I say 12 has a factor, 12 has a factor 6, 12 has a factor 2, so I can break down this composite number into two other numbers, right? In the product of two different numbers. Similarly, if I have obtained the factors of the polynomial, I can write the polynomial broken down into the product of two factors. So k, you should multiply what should lie inside, x square minus beta x minus alpha x plus alpha beta, right? So ax square plus bx plus c should give you k x square minus x is common plus alpha beta. Now see, ax square plus bx plus c, need not forget to put it implies symbol, is equals to k should intrude into every term, k alpha plus beta x plus k into alpha and beta. Now, if you compare, on comparing the terms, a is equals to k, right? A is equals to k because x square is in place of x square. So what is in place of a here? K. Because this polynomial and that polynomial, they are the same things. We are just comparing the places. B is equals to minus k alpha plus beta, and c is the constant. C is k into alpha and beta. Now, what topic did we study, children? We were studying relationship between zeros and coefficients. Coefficients are a, b, and c. A and b and c. C is a constant, not a coefficient, but a and b are coefficients. And zeros are alpha and beta. So why did we get k here? We have to have some substitute for k. So in this second term, I can write in place of k, can I write a? Yes, into alpha plus beta. In the third term, in place of a k, can I write a? Yes, of course, into alpha beta. So alpha plus beta is equals to minus b upon a, and alpha beta is equals to c upon a. So this is the relationship between the zeros of a polynomial and the coefficients, that is the sum of the zeros. Sum of zeros is equals to negative of b. B is what? Coefficient of x. Coefficient, it is